Okay, welcome to another GIA Knowledge Session. I am Karen Smit and I will be your host today. Before we get started, I have a few logistics. I want to apologize for the sirens in the background. I'm here in the middle of Manhattan. So everyone attending today's seminar is going to be automatically muted. If you have a question, please submit it using the Q&A feature you'll see at the bottom of your screen. Please feel free to ask any questions as we go. And then there'll be a Q&A session at the end where you'll have a chance to ask our speaker any questions. We'll be sending a recording of the session to you later today, and that message will also have a survey. We'd love to hear your feedback about any of the discussion that we have today. So today I am joined by my friend and colleague, Dr. Mike Breeding. He will be talking to us about natural green diamonds. So green diamonds are beautiful and among the rarest of all colored diamonds, but can they actually be separated from their treated counterparts? So Mike is the ideal person to be speaking to us today, as he has been conducting research on green diamonds for quite a number of years. And he recently wrote a review article on this topic in Gems and Gemology. So with that, I'm going to pass it over to you, Mike. Thank you.
Thank you, Karen, and thank you to everyone for tuning into our webinar this week. Let's get this started here. So it's kind of funny because I love diamonds, obviously, as a diamond scientist, but green is also my favorite color. So when the topic of green diamonds comes up, it's really right up my alley. It's about as good as it gets. But not just for the color. Green diamonds are quite unique in where they get their color. As you probably have heard from previous webinars or otherwise, most diamonds grow very deep in the earth, anywhere from 200 kilometers down to 600 kilometers down. And most diamonds inherit their color somewhere in those deep depths in the earth, either when they crystallize or shortly thereafter. Green diamonds, however, for the most part at least, don't get their color until they're brought very, very near the Earth's surface at much lower pressures and temperatures. And this kind of makes them cool because this is not the color they started out life with, but this color is only a product of extremely rare conditions in the environment that allow them to gain this extremely rare appearance that makes them extremely valuable. So with that said, perhaps the world's most famous green diamond is the Dresden green diamond. You can see it here in several of these images. It resides in the Green Vault in Dresden, Germany. It's perhaps disputably, but perhaps the largest green diamond ever discovered at nearly 41 carats. It is natural color. On top of its very rare color, it is a type 2A diamond, meaning it is very pure and has very few impurities. On top of that, it's also basically flawless, no inclusions visible to the eye at all. It has a documented history that goes way back to 1741, which predates any sort of diamond treatments. So we know its color is genuine. And as a little tidbit on the side, in the diamond community, we're really fortunate to still have this diamond around, because if you follow the news at all, late last year, there was a heist in the Green Vault in Dresden, and a lot of very famous jewels, including some very large diamonds, were stolen. Fortunately, the Dresden Green was on display in the Metropolitan Museum in New York at the time, so it was not taken as part of the heist. So the world still has this diamond available to them. Perhaps the world's most expensive green diamond, though, is this one you see on the left, the Aurora Green. It's an absolutely beautiful, vivid green color. Little over 5 carats. This is a type 1A diamond, meaning it has some nitrogen impurities in it. But most impressively, in 2016, this diamond sold for $16.8 million. So right around $3.3 million per carat, which is easily the record for any green diamond sold at auction. So from the largest, most famous to the most expensive, green diamonds really hold their place amongst the colored diamond world. The question then comes, where does this green color come from? And through several slides, we're going to get into that. But the gist of it is, it's a product of imperfections or defects in the diamond structure. So here you can see a simplified version of a diamond atomic structure, all carbon atoms in a nice regular arrangement. And they absorb light in a way that makes no color whatsoever. So you get a beautiful colorless diamond. If you expose this diamond lattice to radiation, some of those carbon atoms get knocked out of their lattice positions and they leave empty holes, or what we term vacancies. These vacancies affect the light in a way that produces green or a bluish-green color. They absorb certain amounts of light and let others through. And this is where the color comes from, not just in green and blue diamonds, but with all colored diamonds. It's related to how the defects interact with light. But with green diamonds, we're worried about vacancies or missing atoms for the most part. So how does that work exactly? I mean, most people aren't exposed to this sort of thing a lot, so I put this little diagram to try to illustrate. The way light absorption works is there's light or incident energy that comes and it interacts with the diamond, and then some of it's absorbed by the diamond and the rest is transmitted. And obviously whatever's transmitted is what you're going to see. So in our example, visible light is made up of the entire spectrum of colors. When it interacts with a green diamond, all of the blue and the red part of the spectrum are absorbed by the diamond itself and they stay there. The part that comes through to our eye is the blue to greenish area, and that's why the diamond looks green to us. So that's the basic explanation. As scientists, we use spectrometers to actually collect data that illustrate this. And if you've heard of UV visible absorption spectra, that's what this is representing. So here in this graph, as you go upward, you increase the amount of absorption. And along the bottom are the different wavelengths of light. And I've overlaid the rainbow here so you can see the range of visible light and where it falls. The higher this curve is, the more light's absorbed. So you can see this peak labeled GR1, it stands for general radiation 1. That is the defect that is responsible, or that is represented by those individual vacancies, those missing carbon atoms. And it absorbs the strong peak and this whole broad area. So the whole bit of the red spectrum and also a little bit of the blue spectrum are absorbed just by these vacancies. So in the case of this diamond, sort of bluish green diamond shown, you can see that the low area is this wide range here, which is in black dotted lines on the spectrum at the bottom, shows you it's more of a bluish green color. This is a type 2 diamond with no nitrogen impurities. If you have other things going on, like nitrogen, it absorbs very strongly out in the blue region, combined with the vacancies that absorb in the red. You get this dip here, which is shown in the green outlined box down here now, which is in the green part of the spectrum, and that's how we get green diamonds. Most green diamonds are a product of combination of nitrogen absorption and vacancy absorption. So at least it gives you an idea of why the diamonds are green. So how do we get this radiation source that generates these vacancies in diamond? Well, you have to look at radioactive decay in general to understand. And I know this slide is a bit busy and I apologize, but there's some basics that if you kind of follow my cursor here, hopefully will make sense. There are three main types of radiation: alpha radiation, beta radiation, which is also termed electron radiation, and gamma radiation or gamma rays. Each of those penetrates differently in materials. Alpha radiation is a very shallow penetrator. It only goes a little bit into diamond, whereas beta or electron irradiation goes deeper, and gamma will go all the way through the diamond itself. The type of radiation dictates what your diamond looks like in nature, and you'll see from the coming slides what I mean by that. But I want to point out a couple more things while we're here that are going to be relevant to upcoming slides. The most common source of radiation in the Earth is thought to be uranium. And uranium has a very long half-life of 4.5 billion years. So diamonds have to be exposed to uranium for a very, very long time to develop a green color. And if you look at the abundance of uranium in the Earth, you see that in the Earth's mantle where diamonds form, it's very, very low, about 0.02 parts per million, which is tiny, tiny amount of uranium. But in the Earth's crust, in the shallower regions, it's much higher, on the order of approaching 2 parts per million. So if you were going to come into contact with uranium, it's much more likely to happen in the Earth's crust. Over to the right, you see this crazy set of little figures that represent the uranium to lead decay scheme. Uranium, everything starts as uranium in the top and ends as lead in the lower right. And there's all these intermediate products, but all I want you to take away from this is what's circled in red. And each of these transitions are alpha decays, meaning alpha particles are emitted. So remember I said alpha particles are shallow penetration. So almost the entire scheme of uranium decay involves alpha emission. So it stands to reason that diamonds are going to be exposed to a lot more alpha radiation than any other kind. So does that actually play out in nature? Well, we'll see in a couple of slides. This is just kind of recapping and giving you some examples. Alpha irradiation, very shallow coloration, very near the surface. And you get these little blotches of color right near the surface of the stone. This is a cross section on the right. Whereas beta or gamma irradiation, you can penetrate further into the stone and you can get internal color zones that I'm going to refer to as body color, meaning that the stone itself is actually green or bluish green. And this designation is very important because I showed you that the vast majority of the decay in the Earth is by alpha. So by all rights, you should get mostly very shallow color zones, and very rarely would you get these deeper body colors. So if we look at some naturally irradiated diamonds, this green diamond here, you can see lots of patches of green color on the surface. The interior looks pretty much colorless, right? And if you zoom in and you look, sometimes they're brown, sometimes they're green. You see these very irregular patterns. These are areas of radiation damage. And the majority of diamonds that you see, both green and otherwise, the radiation damage is concentrated very near the surface. Occasionally, and the very, very prized stones like the Dresden and the Aurora are stones that have not only surface coloration, but body color. And you can see from the stone on the right that has been blocked and preformed so that the faceting process has started. You can see that not just the surface, but the interior of the stone is green as well. These are the highly prized stones because they are very, very rare because of the circumstances within the Earth that I went through. It's really important that you understand this if you're manufacturing diamonds and faceting them. This example at the bottom, you have a rough diamond with primarily surface coloration. It blocks and there's a little bit of green, but as you finish it and you take the surface areas off, the stone's basically near colorless, as opposed to those with internal color zones or body color, where despite the blocking and the faceting, you maintain the strong green color. So hopefully this gives you an idea. There are many, many diamonds in the world that have these surface color zones. There are very, very few that have the internal body color, and that's what makes them so valuable. So in natural environments, you would expect diamonds to have the possibility to be exposed to radioactive sources or those alpha, beta, gamma type radiations in a couple of different ways. One, the diamond could be embedded in its kimberlite host, and there may be radioactive grains, little grains of a mineral called uraninite or others that have uranium in them and they decays right next to the diamond. And so it would make these little sort of isolated radiation damage areas. So this is fine and all, but this kimberlite comes from the Earth's mantle and it's bringing minerals from the Earth's mantle. And we saw that the abundance in the Earth's mantle of uranium is very, very low. So this is less likely to happen than shallower in the Earth, where a diamond gets eroded from its host and incorporated in some sort of a sedimentary environment where it's a mixed little pebbles and other things, and groundwater flows through. And this groundwater may have sampled large bits of the Earth's crust and accumulated a lot of radiation. And as a result, these fluids constantly interact with the diamond. They give it a nice rind around the outside, we sometimes call green skin. And here's a picture of a diamond in a conglomerate matrix. You could get an idea there's probably groundwater that is flowing through here quite often. And if it's radioactive and it sits there long enough, you may develop color zones like those on the right. You can see the surface fractures in this diamond are very, very green. They've been exposed to a lot of fluid. This is the way that scientists think that the vast majority of natural green diamonds get their color, simply because of the abundance of uranium and the tendency of green diamonds to be found in alluvial environments, or environments that are sedimentary, where they've been weathered from their kimberlite host. Here's an example of this. On the right, you see some photos from alluvial diamond mining. By alluvial mining, we mean the diagram on your left. You notice there are the kimberlites as they're placed in the earth, and this is where the diamond would be embedded in the kimberlite. Over time, those weather out, and the diamonds, which are very resistant and heavy, they wash into sediments, and they get relocated into deposits that are later mined, sedimentary deposits. But diamonds can sit in these environments buried for millions of years. And over that time, the groundwater circulates and causes these green color zones, both internal and surface. So it kind of gives you an idea of why most green diamonds are found in alluvial environments, and also why you need alluvial environments in order to get green color. So these surface color zones, we call them in gemology typically radiation stains. It's kind of a silly term, but it's referring to brown and green spots on the surface that's from natural radiation. And they come in all sizes, shapes, and forms. If you look here, some examples, some spray out in fractures, some make irregular patterns on the surface. And like the image I showed you earlier, there's both brown and green spots here. But notice they penetrate to a very shallow depth, indicating that this is an alpha particle irradiation. If we look at some more, we can get some interesting information. Here you see all sorts of green stains embedded around in different fractures in the diamond surface, or in different patterns along the edge. The one that's particularly interesting to me is the one in the upper left, where you see sort of these round outlines, outlined by all these little spots of green. And if you remember back to my image earlier, you can easily envision each of these rounded areas as being a class of another material. And the fluid flows around that material and interacts with the diamond. So the middle part's kind of armored by the inclusion, and the fluid's able to touch the diamond around in the other areas. And you may look at these and you say, those look very rounded. And most radiation stains in most of these images are very rounded. They're sort of spots. When I say that a fluid interacts with a diamond, I'm not saying that the radiation necessarily comes just from the fluid, from the diamond stewing in the fluid. In many cases, these radioactive fluids will deposit little grains of radioactive salts onto the diamond surface or adjacent to the diamond surface. And over time, those salts, their uranium in them, will decay and give off radiation that causes this. But they can't get there without the presence of the fluid bringing them in the Earth's crust. So if we explore radiation stains a little further, these areas of natural radiation, we see both green and brown, and we really want to understand what the difference is. So we've done some experiments, and this is kind of a fun little time-lapse video. Don't worry if you can't follow everything that's going on. It's a little busy, but just focus on the color. And down here, you can see the temperature increasing. We heated this diamond to see what would happen to these stains as we increase the color. Before I show you this, don't go heating your green diamonds. This is a permanent change. And if you like green diamonds as I do, you don't want them to end up the way this one's going to end up. So here we go. And it's about 40 seconds. You see the temperature is going up, 350 degrees. Up here, you can see some reference we have for the color changing, and you see that the line is going down, indicating the color is changing as we go. We're up to 500 degrees now, and we're going to start to see a change. Keep your eye in here. Oh, it's starting to get browner. These green stains are changing color with heat. And at 600 degrees, we hold it at 600 for a little while, and we see very, very quickly, within half an hour, the stains go from green to completely brown. And as I said, this is not a reversible change. Once the stains go from green to brown, they never come back. And so here's the original green after reaching 600 degrees, and then after 600 degrees for several minutes. And if we look at absorption spectra, remember I said that this whole area is the vacancy related absorption. When it's green, there's a lot of absorption, and that absorption slowly decays down so that you just have a general pattern which produces a brown color. So now we've established that at about 600 degrees, green stains will turn brown. So this is in a laboratory, mind you, but it stands to reason that the same thing would happen in the Earth, maybe not necessarily on the same time scale, but it explains how we could get diamonds where like this, where we have green and brown stains together at the same time. This has to indicate that we've seen more than one stage of irradiation. It may be the same radiation source, but it has to be happening over long periods of time. This diamond is really neat because if you look closely, you see that all of the brown stains and the green stains next to them have exactly the same shape. That suggests that this diamond actually moved relative to its radioactive source. So you can picture a grain sitting here. It irradiates this diamond. It makes a green spot. And then the temperature changes, or a long period of time passes, and that green spot turns brown. The diamond moves a little bit, and the same radiation source is now touching this spot. And over time, it makes another green spot. And this green spot was never exposed to temperatures above 600 degrees before it came out of the Earth, so it stayed green. So by looking at things like this, we can learn a little bit about the geologic history, even the localized movement of individual diamonds in alluvial environments. It's really kind of cool what you can learn just by looking at these spots. And you see the one on the right has multiple examples. I've drawn arrows showing that they're all in basically the same direction, indicating the whole diamond was moving the same way. But you have a brown spot, a green spot, and then it moved a little more in another green spot. So a lot of interesting information from looking at these radiation stains. What does all this mean geologically? Well, the diagram on the right is fun because it's a cross-section of the Earth. That's easy. But to understand it, you've got to look at the complicated one on the left, where we have depths increasing downward into the Earth and temperature increasing to the right. And all of these gray lines represent different places in the Earth, different areas where as you go down inside the Earth, where you to drill a hole down and measure the temperature, it changes differently depending on how thick the crust is and that sort of thing. In these deep areas called cratons, where most diamonds form, the temperature depth pattern follows a pattern, or profile follows a pattern similar to this. And if you go along that line to 600 degrees, where we've seen that the green stains turn to brown, and you go over here and you find the depth, it's about 50 to 60 kilometers. On the right, I put a red line in showing where about 50 to 60 kilometers is. And you see that is far, far shallower in the Earth than down here at the 150 to 200 kilometers where most diamonds form, showing that in order to get these stains, this radiation damage, these diamonds have to be transported much shallower in the Earth, must be above this red line before they can even get this green coloration. So it's just further proof, looking at the surface damage and the experiments, to show you that this green color can only be inherited at very shallow regions in the Earth. And it's really cool geologically because, like I said, when the diamond formed down here, it was not green. It was not green until it got way up here. So kind of fun geology to go along with the color. We like to investigate these radiation stains, these indicators of natural radiation. And one of the ways that we've done that is by looking at the distribution of defects. This GR1, remember, is general radiation 1, or the vacancy defect in diamond that causes the green color. And if you take a fancy spectrometer that can take tens of thousands of spectra all across this region, you can create a false color map, which is what these little brightly colored regions are. And I took this green stained diamond underneath, and I picked a surface and I did a map of it. And on the right, you can see the zoom in of the area, and I've kind of outlined so you can see the green stains underneath. And then if you look at the corresponding false color map, you see that the stains themselves tend to be blue, meaning they don't have very many vacancies. The diamond is so damaged in the area of the stains that it doesn't really have many vacancy defects, but adjacent to them is where most of the color in the diamond itself is formed. And that's what these bright red areas are. This seems a bit complicated, but why I'm showing you this is, remember I said that most surface damage was alpha related, and alpha particles don't penetrate very far into diamond, but we want to know just how far they do. So by doing this research, we can measure the width of these areas of radiation damage adjacent to the stains, and we find that they're between 18 and 22 micrometers, so very, very small. And this is for a green stained diamond. I did the same thing for a brown stained diamond, and you go in and you look and you start to measure the widths, and you get the same types of numbers, 18 to 20, something in that range, which shows that over time, these diamonds are being exposed to the same type of alpha particles with the same depths of penetration. So it's reinforcing all I showed you earlier through experiments and understanding the distribution of the defects related to the green color. And it's that, even though the stains have turned brown, the diamond still has a green color because of these radiation defects that are adjacent in these narrow, narrow zones. So hopefully that gives you a bit more of a handle on what causes the surface color in most diamonds. So having talked about that now, we look a little bit about where do all these green diamonds come from? Well, these days, most green diamonds are coming from places like South America, Brazil, which is actually where the Aurora green was mined from. And there's a lot that come out of Guyana as well. And here are some examples from an excursion the GIA took to Brazil. These are diamonds straight from the diamond mine. You see all the green color, most of which is on the surface, but some does penetrate deeper. Another spot that a lot of green diamonds are coming out of these days is Zimbabwe. And if you know much about the diamond industry, you know that Zimbabwe diamonds are quite controversial. There were a lot of conflict concerns in the area, particularly in the Marange diamond fields. A lot of that has evolved since then. The U.S. for the longest time, and I think still has an embargo on Zimbabwe diamonds, simply for that reason. But the diamonds from Zimbabwe are really unique in that they have been exposed to a lot of radiation damage, but also they have a lot of natural impurities, things like hydrogen in them. They cause them to be sort of this grayish brownish color, but they get their green tone from the radiation damage. And you can see several different piles here. These are diamonds that we looked at firsthand that came from Zimbabwe. So a lot of greenish colored diamonds, though not so many of the pure greens that you get from South America. A lot of green diamonds have also come out of Central Africa, the Central African Republic. Very nice green stones, and in particular, this diamond on the right is known as the Ocean Dream diamond. It's probably the world's most famous sort of bluish green, greenish blue diamond out there, but it is colored by the same types of radiation defects, and it's radiation body color, meaning that the radiation has penetrated through much of the stone. So I showed you the Dresden earlier. The Dresden green diamond is thought to come from the Golconda region in India, and there are other green diamonds that have come out of South Africa. So I don't want to make you think that diamonds only come from South America, Central Africa, and Zimbabwe. They come from everywhere, but the vast majority of them and the deepest colors tend to come from these areas. So if we look at this diagram, there's a lot of diamonds on here, and I want to emphasize to you that all green color doesn't come from radiation. Most of it does, and you see along the top row, these diamonds, this range of colors, these are radiation-related colors. And it gives you, I mean, if you contrast that with the other diamonds underneath, you see nothing else has the vibrant greens or bluish greens that radiation colors do. So the most prized green diamonds are coming from these radioactive fluid interactions shallow in the earth. There are other defects like the H3 defect, which is a pair of nitrogen atoms and a vacancy in the lattice together can produce sort of yellow-green diamonds of a wide range. Hydrogen defects themselves can produce some green color, though it's generally very brownish or grayish. And then even very rare impurities like nickel can impart a little bit of a green color to diamond. So there are other ways that you can produce some green color, though radiation produces the best green color by far. So this is kind of the same thing. These are the 4 causes of color in green diamonds. And I'm just showing you a range of colors here, and that the defects responsible are different. So vacancies versus nitrogens combined with vacancies in single defects, hydrogen and nickel. And I show you this slide mainly as a lead into the next slide, because I showed you absorption spectrum. Remember, as we go up, you absorb more light. The low areas are where the light's transmitted. And in red here is the radiation. You see our dip right here in the green, gives us the green color. The other mechanisms all look different. The H3 defects absorb light to make yellow color, but at the same time it gives off light that causes this dip here in the green that gives us a bit of a green color. Nickel absorbs in different areas to give green color, likewise hydrogen. So by looking at the way that light is absorbed, you give me any green diamond, if I can measure how the light's absorbed, I can tell you exactly what's causing that absorption. And from that, geologically, I can get an idea of how it obtained its green color. So absorption spectra are very valuable in differentiating what defect is responsible for the color and in what way. If we look at a couple of the other more common causes of green color, H3 that I keep mentioning. So you see the body color of this diamond on the left is yellow. But if you look, you see these green sort of ghosty looking regions. That's green luminescence. So the diamond is fluorescent. This H3 is fluorescing green to visible light. At the same time, it's absorbing to make yellow. So the combination gives you a yellow-green colored diamond. It's really kind of cool how you can get green color from a combination of absorption and emission, or light being given off. Hydrogen-rich diamonds have these features that are unique to hydrogen impurities. You see these little sort of flower petal-looking patterns. These patterned clouds are very, very common in hydrogen-rich diamonds. Sometimes they're even called asteroided clouds. They're so sort of star-shaped or flower-shaped. But you see even on this diamond, green and brown stains on the surface. So it's a combination of the two to give it its color. So what sort of green diamonds do we see in the laboratory? Well, we have to kind of take a look at the distribution of stones. And this is a rough distribution of green diamonds that were submitted to GIA over about a decade. On the left, you can see this pie chart gives you an idea of colors. Most green diamonds are some combination of green and yellow. And this stands to reason because most natural diamonds have nitrogen impurities, and most nitrogen impurities cause yellow color. So if you have radiation damage or another mechanism along with that nitrogen color, you get a green and a yellow combination. About a quarter of the diamonds were pure green. These are most likely diamonds that are just radiation related color. And then a small number are green with a blue component. And these are almost always radiation related. And the last bit have some gray or brown in them, which would be more of the Zimbabwe type green diamonds. So you see, the blue component makes up a very, very tiny percent overall. Most of the diamonds are green or green and yellow. The diagram on the right, you have to pay a little attention here because there's a lot of lines going on. Let's not look at the pie so much as the lines around the outside, because the pie shows all the combinations of radiation plus H3 plus hydrogen plus everything else. The lines, for instance, this line, it encompasses 62% of the diamonds that are submitted to GIA over a decade. 62% of those diamonds have a component of their green color, a major component, due to radiation damage. So that gives you a much better idea that the green color in over 60% of the diamonds with green color are submitted is due to radiation. So only a tiny little bit, for instance, is due to nickel. It's just trying to give you an idea of how many green diamonds are caused by radiation versus other factors. So we've gotten questions in previous seminars, and it's of particular interest to me because, you know what, everybody likes something that changes color. And there is a type of green diamond called a chameleon diamond that will change color. In this image here, you can see that on the left, we have a whole suite of greenish diamonds ranging from yellowish green to grayish, brownish green, that sort of thing. If we heat those diamonds to about 400 degrees C, or if we take those diamonds and we put them in the dark, like put them in a safe, completely in stone paper, completely removed from the sunlight or room light for a long period of time, they will change color. They will go to yellow or yellow orange. And it's really a crazy transformation because this is quite a difference here. But it's fascinating, and these are really popular collector stones because of this. Fortunately, unlike my radiation stains that turn brown, this color change is temporary. It only lasts for a few seconds, actually. So if you put a stone in a safe for a month that's this color, you open the stone paper and you see this color may be gone in a matter of 1 to 2 seconds. That's how fast it changes back. When you heat them, it takes a little longer because they're cooling, but it still changes back in the course of several seconds to a minute. So in an effort to try and show you an example, this is diamond's a little bit dark, but it was the one that we had available. So this is a greenish chameleon diamond, and I'm going to play this video. You're going to see the temperature increase up here listed, and you'll see the color change. So here we go. We're at room temperature. We move up to 70 to 150 degrees, and you see the diamond lightening color, 250 degrees. Once we hit 300 degrees, you see this diamond is a yellow to yellow-orange color. If I turn the heat off and just let it sit, in a matter of about 30 seconds, this diamond goes back to its original greenish color. So same thing happens in the dark, but it's just an illustration to you of what actually happens. Now, this is really cool and it's fun for collectors, but I have to warn you, just as I did with the radiation stains that's permanent, this is not permanent as long as you're using something you know is a chameleon diamond. Most of the other green diamonds will permanently change color if you heat them like this. So I don't recommend you do this at home, simply because the last thing you want is to take a green diamond and end up with a yellow diamond after. So it's fun, it's good, and we do test this property in the laboratory when a diamond's sent in. If it qualifies for a chameleon, we put a comment on the report. So that's sort of the easy way to know what you're dealing with. So that then if you want to heat it yourself, you've got an idea. The other thing is if you heat these diamonds too high, you can also change their color permanently. So you've got to really control what you're doing. But they're fun collector stones, and not just that, they have some really unique geology and mineralogy associated with them. These are deep UV, or if you've heard of diamond view images, this is fluorescence that's coming out of the diamond. And my colleague Ulrika talked about fluorescence in one of the previous webinars. And the cool thing about chameleons is if you look at their fluorescence, you notice quite quickly they're very heterogeneous. They have these areas with this sort of greenish yellow fluorescence and these areas with either inert or blue fluorescence. And this is almost always the case, be it in patterns like these or banded. And the cool part is the only part of the diamond that changes color, if you look in the microscope, are these greenish yellow fluorescing areas. So the difference in the quality of the color change in most chameleons has to do with the distribution of this zone, these growth zones, relative to each other. Turns out these greenish yellow zones have a much different composition than the blue zones. And if you start to look, and I should also mention that Ulrika talked about phosphorescence in the previous webinar. Only the greenish yellow fluorescing zones phosphoresce. And this is a very important property of chameleon diamonds, but it's only this part that changes color and phosphoresces. If we start to look at the spectroscopy of chameleons, we find, and you can see in these two different types of spectroscopy, the upper left is visible absorption. The red line is a hydrogen-related diamond. The purple line is a yellow diamond colored by a 480 nanometer band. The middle spectrum is a chameleon. And in both cases, if you combine the spectrum of the hydrogen diamond with the yellow diamond, you will get a chameleon spectrum. Much like if you combined the color of a hydrogen green with a yellow orange, you get a chameleon color. So I think what's going on with chameleon diamonds, the reason they exist is because of this complex intergrowth, this different stages of diamond growth together, all in one stone, that give you this really unique property. So it's just kind of a fun bit to take away. So the other bit of this talk were natural versus treated color. And so you see these two diamonds, and it's really hard to tell which one would be natural and which one would be treated. And that's a lot of what we deal with in the lab. In fact, if we look at the spectroscopy, here's the absorption. You see the absorption window in the green for both spectra. The top one is a treated green. The bottom one is a natural color green. Separating these two is probably the single biggest challenge in colored diamond identification right now. And we are doing extensive amounts of research because we can't always make this determination. That's very frustrating to us as a laboratory because we want to be able to. So I'm not going to be able to give you definitive answers. because while we cannot identify every diamond, we are able to at least tell you if we can or cannot identify them diamonds, which is good. So if we can't say natural or treated, at least we know that we can say that we're not sure. And that's what sometimes you'll get an undetermined call on a GI, a colored diamond report for a green diamond. It's because we're still working to understand this better. I'll show you at the end here, though, we've made some serious strides, and the majority of diamonds, green diamonds sent to GIA now, can be given a color origin, which is fantastic, and it's a product of high quality research. Historically, irradiation treatment has been done for a long time on diamond. In fact, we put these together because the first way that it was done was by immersing a diamond in radium bromide salts and just leaving it there for a long time. So these highly radioactive materials interact with the diamond and produce some green color. I really love this because radium bromide was discovered right around 1900 by Marie Curie. And then in about the 1920s, there was this crazy craze that went on, completely crazy, where it was being touted as a cure-all and it was being sold as medicine. See here, dosage, take 2 tablets night and morning, and it was supposed to cure pretty much anything that ailed you. So ingesting all this radiation certainly did not help anyone. But that's how long ago, 1920s we're talking for this sort of thing. And the diamonds, there's still a few around. Here's one on the left. They tend to have these very bright green spots from contact with the radium salts. And they also tend to be a little bit radioactive. Now, that being said, I think I've seen one of these in my 16 plus years at GIA. So they're not exactly common. So you don't really have to worry about your diamond being radioactive at all. When we say it's colored by radiation, it's just that the vacancies are created. It doesn't mean there's any radioactive material left in your diamond for the most part. So you don't have to worry about wearing your green diamond and getting your skin irradiated, like you might have to worry about if you decided to take 2 tablets night and morning of radium bromide, which do not do, please. So over time, large-scale instrumentation was built that accelerated charged particles. The cyclotron, which was developed at UC Berkeley in about the 1940s, was used to concentrate charged particles in a way to bombard diamonds with them. And if you're familiar with cyclotron green diamonds at all, they have this very infamous umbrella structure that you can see at the culate where the color is zoned. This is just due to the way the particles penetrate the diamond and then the stone is relative to the stone's faceting. So if you heat a green diamond, you can turn it yellow and you'll still have the umbrella effect. That's why there's a yellow version here as well. Diamonds can be irradiated by gamma rays. When I mentioned earlier, it's not very common, but it can be done with radioactive sources like cobalt-60 or in a nuclear reactor. These tend to take much longer periods of time and have much shallower penetration and color depth. They're really not done just because of the danger associated with the radioactivity involved, as well as the time and the lack of a quality product. These days, almost all diamonds are artificially irradiated using an electron beam or an E-beam accelerator. Here's an example of a facility where the electrons are accelerated and channeled down through this device. The diamonds are put on the table and the electron beam is scanned across them, and it causes coloration to form. Diamonds will heat up in this process, so they're usually put on a cooling table, and they're usually put on table down. And a byproduct of this is that most artificially irradiated or lab irradiated diamonds tend to have color concentrations in them. And if you look, you'll see often those color concentrations near the culates of the stone based on the way that they're irradiated. So here's a bluish one, a greenish one, and you can see on the lower right a pink and a yellow as well. These are from other treatments where they heat the diamond after they irradiate it. Now, technology's improved a lot, so they don't have to leave these color zones on here anymore, unfortunately. You can get much more even coloration or body color through these types of electron irradiation experiments and treatments. So if you see these, they're good indicators, but if you don't see them, it doesn't mean your diamond hasn't been artificially irradiated. What we do to try and understand this better is we take our own samples. So we take natural diamonds, we cut them into many pieces, and then we irradiate them ourselves under known conditions, low irradiation doses, higher irradiation doses. We even send them to facilities that do commercial irradiation, and they won't tell us exactly what they do, but they give us a product and we can see before and we can see after. And by doing that, we can see the changes that go on. So here along the bottom, you see these are all pieces that were cut from the same diamond, mind you. These three were the befores, and you see the very little absorption. It's slightly brownish, no major vacancies. Low dose of radiation, you get a little bit of vacancies. Higher dose, more vacancies, and the commercial dose, we get a ton of vacancies. And our transmission windows show appropriately green, green, and this one shifts over to the blue because there's so much radiation. So the way that we go about identifying these things using spectroscopy is we do experiments like this, and we look at the changes. And here's an example using a laser emission spectroscopy, a photoluminescent spectrum. The same set of stones, we get a series of peaks before they're treated, and then the peaks get larger as the radiation dose increases, or sometimes disappears if large doses, if the stones have been heated a little bit. So by looking at which peaks appear and which peaks disappear, and with how much radiation dose and with how much heating, we put together sets of criteria. And this is the type of research we're doing to really understand when we see this final product, we don't get to see the beginning. We have to be able to look at what we see and sort of turn into a detective and work back to what it might have looked like beforehand. And thanks to lots of research on green diamonds and radiation, we're much more able to do that now. And if you send your green diamonds to GIA, we have a confidence that if we give you a natural or treated origin, that's what your diamond is. And so you can feel that confidence as well. So with that being said, time's pretty much up here. So I wanted to tell you that as Karin, my host, mentioned earlier, there's an article in Gems and Gemology. It's in the spring 2018 issue. It's called Natural Color Green Diamonds, a Beautiful Conundrum, that me and my co-authors put together. It has a lot of the information I presented to you, along with a lot more information. Have a look. You can go onto GIA's website, the Gem and Gemology part, and look for the spring 2018 issue, and you can read the article and the issue at no cost online. So please go have a look, enjoy, and I hope you've learned a little bit about green diamonds through all of this. I thank you for your attention, and I hope you appreciate these fascinating stones that really get their color in a very unique way as much as I do. So thank you.
Thank you very much, Mike. That was a very entertaining talk. Thank you. So I have a few questions from the Q&A session that hopefully you'll be able to answer.
Sure.
Okay, so one of them is someone who is asking if GIA confiscates radioactive treated green diamonds. They're also asking whether all green diamonds are radioactive and if there is a danger threshold to this radioactivity.
All right, so I'm going to answer the last part of that first. I mentioned it a little bit later in the talk. I should have mentioned it earlier on, but when we say radiation-related color or radiation green diamonds, no, they are not radioactive. The radiation is present. It causes the vacancies, the atoms, to be displaced from the structure, which causes the green color. The radiation itself doesn't cause green color. There is no radiation in these diamonds. The radioactive material is long gone. All that's there are the missing atoms, which absorb light to create the green color. That being said, there are, once in a blue moon, some of these radium salt colored diamonds that'll come through. Like I said, I've seen one in 16 years, and they will test a little bit radioactive with a Geiger counter. When that comes up, being a scientist, I escalate things to our folks who interact with the government, and we discuss this with the appropriate authorities as to whether or not anything needs to be done. So I can't really tell you exactly what we done. We don't confiscate anything. If anyone confiscates anything, it might be the government. We just make the appropriate authorities aware that this is in existence, and they work with the client to resolve the issue. So hopefully that answers that.
Another question that we have is, does having a very strong green fluorescence impact the appearance of green diamond, and does it impact the certification grade or the color that's reported? So
the color that's reported for GI colored diamonds is measured in conjunction with the same lighting environment as all colored diamonds. So if, for instance, those H3 colored diamonds with the green luminescence, if that luminescence is stimulated by visible light, that's emitted from the grading environment, you see the green, it becomes a part of the color, yes. So those diamonds have yellow body color with green luminescence, but often get green or greenish yellow color calls on reports, because in the grading environment and in daylight, that's what they show. The green luminescence definitely is visible because it's stimulated by visible light, which you can't really get away from in a room or outside. Does it affect the appearance? It's a bit of a difficult question for colored diamonds, simply because they're colored. And so yes, it's contributing to the color. Other fluorescence issues in colorless diamonds, where we have strong blue fluorescence sometimes affecting the color, that's a bit of a different situation, because that fluorescence isn't stimulated by visible light the way the green is. So hopefully that answers that.
And so we also had some questions about radiation in nature and what other radioactive elements there are, for example, potassium, rubidium, thorium, and whether those decay of those isotopes can also affect the color. And I was wondering if you could then also just talk a little bit about, like the radioactive fluids and where in the Earth's crust you could expect these different types of elements that would be decaying.
So there are certainly other radioactive isotopes out there that are present in the Earth. Uranium is generally thought to be the most likely culprit for a couple of reasons. One, tends to be the most abundantly available in well-known minerals. And it also has a time scale that's consistent with what we see. But finally, I showed you the decay chain that has all of that alpha decay in it. And since most of the green diamonds we see only have green surface coloration, we know it's related to alpha decay. So it really kind of all makes sense together that uranium is responsible for the bulk of it. There is a lot of potassium, and there's there's thorium involved in various ways out there, but it doesn't, from the research that's been done and the evaluations, it doesn't appear to be of high enough concentrations in the Earth in the right places to actually be interacting with green diamonds in any way as significantly as uranium is. The bottom line is I don't know for sure. Obviously, it's almost unheard of to find a radioactive mineral left in a green diamond. I mean, it has happened once or twice, but it's really pretty much unheard of. So the radioactive fluids, it's important to remember that it takes a long time to impart this type. And we're not talking about fluids that are so radioactive that they're just smoking or anything. These fluids have to stay around the diamonds for either around them for a long time, or they have to deposit their radioactive salts on the diamonds or adjacent to them and let them sit there for quite a long time. We're talking thousands to potentially millions of years in some cases to impart this color, especially this deeper color. To get enough beta or electron radiation into a diamond to create body color like you see in the Dresden and the Aurora, the diamond had to have been exposed for a very, very long time. So.
And then we had two interesting questions about nickel in diamonds. So could you talk a little bit about what you think is the structure of the nickel, what the defect structure of the nickel is causing this color? And also whether you think these nickel-containing diamonds are coming from the lithosphere or the sublithosphere. And then lastly, whether a green diamond due to nickel, because the nickel coloration is so rare, whether you think that these diamonds would be more valuable than other green diamonds.
So nickel coloration in diamond tends to produce more yellow to yellowish green color. You don't, or greenish yellow color. You don't get a ton of green, but you do get some. They're very rare. We see traces of nickel in a lot of diamonds, and presumably that's due to the abundance of nickel in the Earth's mantle. But rarely do we get nickel in a configuration that will cause absorption that produces green color. And I can't tell you exactly what that defect is, because I'm not sure anyone knows what the particular configuration of the nickel that's causing the absorption to get the green color is. I'm not a diamond physicist, admittedly, more of a geologist here, but nickel goes into diamond associated with nitrogen. So it's a combination of nitrogen impurities, nickel impurities, and vacancies. Nickel doesn't fit real cleanly into the diamond lattice, and so it requires those combination of different impurities adjacent to each other in order to accommodate the nickel in the diamond lattice. That's another reason why it's not super common. Now, where it's coming from in the Earth, Karin, you're a resident diamond geologist. You can probably answer that question way better than I can.
Maybe. Yeah, I was thinking about that actually. I think it depends on whether we actually have mineral inclusions associated with the nickel in the diamond. So the only way that we can tell the depth of a diamond, where it comes from in the earth, so lithosphere versus sublithosphere, is to look at the mineral inclusions, have those identified, and we can either determine pressures from those minerals to get the exact depth, or otherwise just the identification of those minerals can tell us whether they're coming from the transition zone, the lower mantle, or the lithosphere. And so I don't think that there have been any systematic studies done just yet on where in the earth these nickel-containing green diamonds are coming from. As far as I'm aware, but I don't think so.
I mean, I will emphasize that nickel as an impurity, at least in trace concentrations in diamond, is not super uncommon. There's actually fairly common in diamond, but getting enough nickel in it to cause color is certainly a unique situation and something that's extremely rare.
Okay, and so we have time for one last question. Could you let us know whether lab irradiated diamonds have green radiation stains, or whether the radiation stains are specific to natural diamonds?
So this is where life is pretty good, but there's a caveat to that. So no, in general, lab irradiation, any type of electron irradiation will not produce radiation stains. The only way you can produce radiation stains artificially is by creating alpha particles. And there are only a few facilities in the world that are capable of doing this. And it's very expensive. It's very time consuming. We have done it. And it's kind of funny because I have a slide where I have GIA written in the table of a diamond in artificial radiation stains. But we have never seen an artificial radiation stain. So you can rest assured that if you see radiation stains on your diamond, they're natural radiation stains. Now that being said, don't get confused, because sometimes you get brown, for lack of a better word, gunk, or contamination on the surface of your diamond or in fractures. A radiation stain sort of, you can see it sort of filtering into the diamond. It has kind of a wispy, shadowy effect as it goes down in. So make sure that what you're seeing is a radiation stain before you assume so. Now, all that being said, if you see radiation stains, you can assume your diamond grew in the earth and was exposed to some radiation in the earth. It doesn't mean that the color is natural. Unfortunately, there are many people who take diamonds with green and brown radiation stains and they put them under electron beams and they add body color to them. And this is all in an effort to defraud the public and the gem labs and to attempt to pass off a diamond that did not have much color, just had that surface green color, add body color to it through treatment and try and pass it off as a natural color, green body color diamond, something that has the vibrant green like the early stones I showed you. And this is why we're doing all the research we're doing, because we can't just rely on seeing those stains on the surface to know that the color itself is natural. So hopefully that answers it. But much more work is ongoing just toward that end. So it's a very insightful question, and thank you for it.
Okay, I think we are going to be wrapping up now. So thank you very much, Mike. Thank you for your time. That was a very informative talk. And so thank you everyone for coming and joining us. Please join us again next week, where actually I will be giving a webinar along with my colleague, Dr. Erin Palke, to compare origin determination for diamonds and for colored stones. So we'll be talking a little bit about geology of colored stones and diamonds and where the country of origin for both are possible. Also, please follow us on social media. GIA is on Facebook, Twitter, Instagram, and LinkedIn. So thank you very much, everyone, and have a lovely rest of your day. Goodbye.
Goodbye, everyone. Thank you.